All right, we're live.
Hello, Jonathan.
There we go. Okay, forgive me for poor sound quality and background noises. All right. So here in the first one, we have nitrogen. Now, what I'm going to do is a bit of a code here. All right. If it's an element, I'm going to circle it green. Okay. And I didn't ask you to do this, but it's just a good idea because it helps us see things. You don't have to use green. Use whatever you want. If we have N2, nitrogen there by itself, element or compound? That's an element. So is hydrogen. If it's a compound, I'll do it blue. We remember that a compound is a pure substance made of two or more different elements combined in fixed ratios. Okay, we're going to level this up in another way too. Atoms, ions, or molecules. Okay, so I just got to find a pen for this. A equals atoms. M equals molecules or molecular compound, and I means it's made of ions, or we could say it's an ionic compound. So there's another code. Okay, so if it's just nitrogen by itself, but it's N2, is that we know that's an element. But if there's two connected together, two atoms of nitrogen connected together, and they're sharing their electrons, because that's what nonmetallics do, what kind of particle are we dealing with here? Atom, molecule, or ion? We can color code these guys too, that's fun. So what have we got? Green, blue. Let's do dark blue for the ion. Purple. Do purple for ions. And pink for molecules. One more highlighter. There we go. Okay. Maybe I'll just color code it. I'm not sure about the pink. Let's go, let's find something that's totally different. Pink's fine. Magenta. That pops. Like that. And I'm just going to put the color code underneath, just so I'm reminding my brain. Sometimes to do better, you got to slow down a bit and take your time. I always find that if I rush, the probability I make a mistake goes up quite rapidly. How many find that if you rush through things, you're more likely to make an error that you're like, I should have got that, right? Okay. All right. If it's N2 by itself, well, that's made up of more than one atom. And if it's just by itself, whoops, then that's a molecule. That's a molecule. That's a molecule. Maybe I'll do it above instead of below. So these are all molecules. Cool. All right, now before we even balanced anything, KClO3, what do you say, element or compound? Element, K is potassium, Cl is a chlorine, and there's 3 oxygens. Yeah, that's a compound for sure. Whoops. Okay, we can make that. And KCl, so potassium and chloride, potassium chloride. Element or compound? Yeah, so 2 different elements. Oxygen just by itself. What do we say for that? Yes. Cool. Sodium chloride, NaCl, element or compound? Yep. So I'm going to speed run this a bit. And wherever I see more than one element, we know that's a compound. So now we can just rip through. We'll start to see that we're dealing mostly with compounds for these things. O2 by itself is an element, but it's also actually a molecule, which is kind of weird. These are all compounds. Mostly compounds. So, and this is how it is in nature. Like, you don't find a lot of pure elements. Okay, Na by itself, that's an element. NaOH compound. We used that the other day. Ag2O, that's a compound breaking into 2 elements. S8. So sulfur as an element actually exists in a form where there's 8 atoms connected to each other. It's kind of a weird layout. SO3 though, that's a compound for sure. Carbon dioxide's a compound. Dihydrogen monoxide's a compound. Glucose is a compound. Magnesium bromide, these guys are compounds. Compound. Now this last one here, 17, is actually a special kind of reaction called a neutralization. So that's if you have an acidic substance reacting with a basic substance. You're basic. Okay. It's a neutralization actually also followed by and including a decomposition. We can see carbon dioxide gas bubbling off there. These are like the old grade 5 volcano project, right? Where you add the vinegar to the baking soda and it fizzes up. That fizz is carbon dioxide gas. Okay, so there's a ton of compounds here. All right, before I even started balancing, I'm just setting the stage for my brain to go, okay, got to start to count things. Yeah, right? So there's very few elements in this picture, which is all right because that's going to give us a hint about the kind of reactions we're dealing with. It's going to make them pop out, and we'll be able to tell what reaction types they're going to be. Now they're all color-coded, and man, they just jump out. There we go. Okay, cool. Okay, fine. Let's roll. Shall we balance the first one? Just by inspection. Now, by inspection just means we look at it and we do quick counts. We say, okay, how many on the left, how many on the right? Add numbers, but the trick is with inspection, sometimes, as you saw down low, we got some more complicated ones, and that can actually get a bit tricky. Okay, so that's where having that extra step, like doing the cloning method or doing the accountant method, which I'll show you in a second with this first one, because it's a pretty easy one to process, and I can show you the different examples, okay? So can we figure out what reaction kind this is? You've got 2 elements forming into one product, one compound. If you look over at the legend on the chalkboard there, that's also in your OneNote, which pattern does number 1 fit? Synthesis, right? Did you get it right? Okay, thumbs up if you thought synthesis out of those 5. Beautiful. Okay, so we're going to it says, to the left of each number below, use the following code for identifying reaction types. So I'm just going to write the letter S there, S for synthesis. Okay, let's rip through these guys then. Okay, I've got one reactant busting up into potassium chloride and oxygen gas. Salim. Yep. D for decomposition. Sorry, did you mind that I identified your name? No, you're good. Okay, cool. Right on. Okay, here we got an element, or sorry, a compound reacting with an element to make a new compound and a new element. Single displacement, all right? So sodium chloride is the couple. In comes fluorine to the high school dance, and out walks a new couple, sodium fluoride, and chlorine is off by itself. So that's a single displacement. All right. Okay. Hydrogen plus oxygen will make us water. We did this. Remember we lit it up the other day and made that pop over and over and over again? So what kind of reaction is this? You got one product. That's a synthesis. But you're also reacting with oxygen. Anything plus oxygen is automatically a combustion. And there's a bunch of them here, so we can kind of speed run those guys. Watch, number 7 is a combustion, but not a synthesis. Number 8 is a combustion, not a synthesis. Number 9 is a combustion. So 7 is the combustion of methane. That's the reaction that's happening when we run our Bunsen burner. Number 7. Number 8, how many have a barbecue tank at home, like propane tank? That's the reaction for burning propane. Now that's if you have complete combustion, you have a high level of oxygen. But when we burn these things on our barbecues or whatever, it's never quite complete. And that's why you get those weird byproducts like soot. And you get, how many have soot on their barbecue? Right? Like if I say, okay, like just you wipe your finger inside the barbecue, you're going to pick up black carbon. Okay, that's soot. So that tells you it's incomplete combustion. But these are the complete combustions. All right, we got phosphorus combusting there. But if we look here, there's only one product. So that's also a synthesis. Right? And notice I'm just skipping through. You don't have to go in order to answer your questions. Do the ones you're confident with first. We're all over combustion here. S8 plus O2, sulfur plus oxygen makes one compound. If it makes one thing, then it's a synthesis and a combustion. So S/C. There you go. Okay, and one final one down here where you've got hydrogen if it reacts or with water. If water reacts with oxygen, you get hydrogen peroxide. Does anyone know what hydrogen peroxide is used for? Yes? No, it's similar. Cleaning, yeah, disinfectant, beautiful, yeah, like an alcohol. It's actually two OHs stuck together, and OH is the functional group of alcohol. So, good thought on that. Now, would you say this is a synthesis as well, or not a synthesis? So we've got two reactants, water and oxygen, combining to form only one product. Does that also make it qualify for a synthesis reaction? Yeah, if we look over there on the board over there. So this is a special case too. But we notice with number 7, 8, and 9, they all have more than one product. So they don't qualify for synthesis. So they're kind of a weird combination. And over on the board here, you'll see my little note that said a combustion may also be a synthesis, but it may not. It just depends on who's involved. Okay. Let's balance by inspection now. Okay, so I got myself a compound. I've got sodium chlorate, it's called, and sodium chloride. So sodium, a metal and a non-metal. What's that going to be made of? Is that ionic or molecular? It's ionic, beautiful. Okay, so sort of dark purple for that one. Don't worry, we'll get to the balancing yet. This, what I'm doing right now, is actually technically review for the retest. Okay, there you go. And potassium with chlorine or chloride by itself. So potassium chloride, is this ionic or molecular? You got potassium metal and chloride non-metal. Good. Potassium cations, chloride anions. Okay. Oxygen's actually a molecule. It's an elemental molecule. So there's 7 elements that exist as molecules. It's kind of weird. Instead of existing as an atom. Sodium metal with chloride non-metal. Is that ionic or molecular? It's ionic. Okay, so where were we? We have a metal and a non-metal. I'm going to do speed run on that. Sodium and fluoride. Lead and hydroxide. Lead and chloride. Aluminum and bromide. Potassium and sulfate. Potassium bromide. Aluminum sulfate. Aha. CH4. Is carbon a metal or non-metal? Carbon's a non-metal, and hydrogen's a non-metal too. So if that's all non-metal, then that's molecular. We know oxygen's a molecule, carbon dioxide's a molecule. There we go. All these are molecular reactions right here. Okay, non-metal, non-metal. And they're going to tell us that covalent bonding is occurring. Okay. And water's a non-metal. Molecular, molecular, molecular. How many see that I'm kind of speed running because I'm on a pattern now? I'm going, okay, I'm looking for all the ones that are non-metals only. And now we can just quickly rip through those. Sodium's a metal. So if it's just a non-metal by itself and no metals around, we know automatically these have to be molecules. Now, special case, potassium and magnesium are metals down here, but they're yellow, meaning they're atoms. Ionic, ionic, metal, non-metal, metal, non-metal, metal, non-metal. Okay, now there's some special cases here. HCl is actually an acid. And acids turn ionic when they hit water. So even though hydrogen is a non-metal, and I'll give you those, you won't have to memorize that, okay, in advance. Those guys actually form ionic substances. Okay. There's a sodium atom. Ionic. I'm going to hit all the ionics. Let's get those out of the way. Let's just do a rip. Wherever there's a metal and a non-metal, that's automatically ionic. Okay. This one's a special case here. And so is that one. And I wouldn't expect you to know these ionics, so I'm going to give you those. For you guys, just if there's a metal and a non-metal, we're going ionic. But we see sometimes there's special cases. All right, now molecules. If there's no metals around, other than those couple special acids that I showed you, these are all molecules. Glucose is a molecule, water's a molecule, carbon dioxide's a molecule. And if you kind of fly over it like this, you start to see patterns. Ah, silver metal. Oh, there's an ionic I missed. Ionic, 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 ionic. Ah, if you got two ionic compounds making two new ionic compounds, what kind of reaction is that? Two old compounds react to form two new compounds. If we look over here on our chalkboard, which pattern does number 10 match up with? You got two ionic compounds. Can we make sure we're awake? Give a nudge. Thank you. All right. See, now it's funny. I'm in on the joke. Okay, it's good. All right. Stay awake, man. Get a coffee. I got you. They wake you up too early. That's my view. You're all like, preach. Okay, so we got two compounds reacting to form two new compounds. All right, have I highlighted them all? I think so. Oh, special case. HCl is actually called hydrochloric acid. It's actually the acid that's in our stomach. It is corrosive. Of course it's corrosive. All right, now we can attack these. All right, so number 5, I've got a compound reacting with a compound to make 2 new compounds. What pattern does that fall? Yes, sir. Double displacement right there. Okay, number 6, I've got aluminum bromide reacting with potassium sulfate to make potassium bromide and aluminum sulfate. Double displacement again. Okay, 7 through 9 are what we call combustion of hydrocarbons. So hydrocarbon combustion reactions are not also synthesis reactions, are they? Because they make more than one product. And in fact, if we don't have enough oxygen, so all 3 of these are what are showing complete combustion. So in this case, this is kind of like an acetylene torch where you've got a full-on oxygen supply. Imagine you had a pure oxygen tank blowing into your campfire. How would that go? It probably wouldn't be soothing. It would look more like an instant regret TikTok video. You know what I'm saying? Hey, don't do that, please. But this is why like normal people can't just go get an oxygen tank, right? But no word of lie, my dude, my friend, he was at a bingo doing a fundraiser for the school, and this lady's smoking a cigarette and sucking on an oxygen tank at the exact same time. He's like, hey, Buck Rogers, you want to put your cigarette out? I'd like to survive. And so would everyone else in this room. Yeah, literally, it could have gone up, right? Mabel could have had a whole new hairstyle, right? That looks a lot like mine. Hey, Martian? There you go. Okay. So normally, these combustion reactions are not complete. We don't have a full crazy oxygen supply tank feeding our furnace, do we? No. Right there. We have oxygen from the air, so most often hydrocarbon combustions are what are called incomplete. And again, we get other products like carbon, that's your soot, carbon monoxide. How many have a carbon monoxide detector at home? Okay, a few of you want to survive. That's great. All right. Oh, good. Okay, more. Okay, hands up. I love it. Okay, that's great. Okay, this is a bit crazy, but we're rolling now. We're cooking with gas, literally. Okay, sodium reacting with water to produce sodium hydroxide and pure hydrogen. So an element reacting with a compound to make a new compound and a new element. What do we call that? Go ahead. You got it?
Sorry, say again.
Well, number 12 here is sodium, Na, reacting with water. That's H2O, right up there. And that arrow says react to form sodium hydroxide and pure hydrogen gas. Single displacement. Good job. Okay, silver oxide reacts to form pure silver and pure oxygen. Shout it out. Well, we're on number 13 now. Decomposition, right? You got one reactant busting into more than one. Okay, 15. Yeah, this is a special case. It's a complicated one. This C6H12O6, that's sugar. And oxygen. What kind of organism can take carbon dioxide and water and sunlight and combine those together to make sugar and then put out oxygen? What do we call that? Plants that do? You got it. Now, they don't do it instantaneously. There's a whole pile of steps that my grade 12 biology class has to learn. Oh gosh. They have to build things one thing at a time, but this is the overall reaction for photosynthesis. Guess what? What did you have for lunch? Nothing. I had a protein bar, whatever. But what do people eat for energy? Sugar, right? Carbohydrates. I've eaten more than my share. That's why I'm diabetic. I earned this one, right? Wasn't born with it. This didn't just happen, right? So photosynthesis, well, we eat sugar and we breathe in oxygen. O2, right? And so the opposite reaction is what we call Yes, my guy, cellular respiration. And where does that happen in our bodies? We're going to circle back to this when we get to the bio unit. No. Lungs is how we get the oxygen into our body. So the O2 is going to go into our blood. Our blood will carry that O2 to our cells and then deliver that O2 to the... No. To inside of the cell. What's the powerhouse of the cell? Not the nucleus. That's where your DNA is. The mitochondria is the powerhouse of the cell. I love mitochondria. Parents, teachers, and honored guests. My speech is on the mitochondria, right? Okay, there you go. Did you guys have to do speeches? No. Oh, you got off the hook. Okay, now I do speeches for a living. Here we go. All right, so we got number 16. Let's rock that. An element, potassium, reacting with magnesium bromide to make potassium bromide and magnesium come out the other end. Yes, sir. Single displacement. Okay, so single element walking into the dance going, hey, bromide. Magnesium's like, yeah, I'm good. See you guys later. And off it goes to go chill with its bros. Okay. This one's special case. We're not going to identify that and that. Okay. These guys here are a combination of a neutralization which is a special, I'll try spelling. A special double displacement. Immediately, followed by a decomposition. So this example is a bit more complicated than I like for grade 10 applied science, but it's great for doing balancing. So reaction types, if they don't fit in that, and that's why I wanted to go through this with you. Okay, so because we had a couple special cases here that I wanted to point out. Okay, we haven't even got to balancing yet, right? Which was the whole point of this, partially. But what's cool is that all this highlighting and identifying allow us to apply all the stuff we learned that we're going to, demonstrate that we've learned again in next week's test. Okay. Let's do a balancing by inspection. So we're just going to look at it, and then I'll do a proof after that. A couple different ways. Okay, so let's look at number 1. How many nitrogen are on the left side, on the reactant side of this skeleton equation, they call it? Skeleton equation. It's appropriate. It's Halloween time. Skeleton equations. It always comes up this time. It's wonderful. It's seasonal. 1 and 2. Remember that test question? The subscript tells you how many there are. Not their charge. So if it's N2, it's a weird element. There's 7 of them. Nitrogen, hydrogen, oxygen, fluorine, bromine, iodine, chlorine, and that's it. Did I say oxygen? Anyways. And hydrogen has 2 as well. But how many are in the product? And this product, by the way, is called ammonia. And I don't expect you to know that, but I do expect you to know that it's been on the board, on the wall over here all the time. NH3. Okay, and I'll leave that up there for you. Okay, just like we don't call water dihydrogen monoxide, we don't call ammonia nitrogen trihydride, but you could name it that. Like if I put it there, that's how I'd want you to name it. Okay? But if you're really savvy and you wrote ammonia, I'd still give you credit for that. Pretty smart. Okay, so how many nitrogens are in an ammonia molecule? And how I know it's a molecule? Because it's pink. It's magenta there. Magenta for molecules. That sounds good. How many nitrogens are in an ammonia? There's just one. Okay, so we got to pull out our multipliers because I got 2 on the left side, but only 1 on the right side. So what big number do I have to put in front of the ammonia molecule? I got 2 nitrogens, N2. That's built in. You can't unbuild that. Okay, pure nitrogen is N2. That's on lock. I got 2 nitrogens here, but how many ammonias are drawn in the skeleton equation? Remember, skeleton equations are just where they draw 1 of each. All right? No multipliers. Sometimes skeleton equations are already balanced. There are certain cases where that can occur. It's almost over, bro. Don't worry. Okay. How many nitrogens do we have? NH3. The subscript tells you how many there are. In ammonia, it's NH3. If there is no subscript, how many are there? 1. Beautiful. Okay, so if I start with 2, I got to end with 2, don't I? I'm going to put a big 2 in front. There's my multiplier, my coefficient, as the science nerds call. Well, if I went 1 times 1, then I'd still only have 1 nitrogen. And that's a fine question, okay? And thank you for asking, right? Okay, as we get confused. But now, here's the deal. That multiplier not only multiplied the nitrogens, it also multiplied the hydrogens, didn't it? What's 2 times 3? So if we go beforehand, we've got H2. Pure hydrogen gas is built in as H2. That's built in. So what number has to go in front of hydrogen? You got it. There. Done. Balanced by inspection. Okay, lucky us, we got it right. But how many feel 100% confident? Yeesh, no, right? Okay, thank you for your honesty. So let's do a proof. Let's balance ammonia. Let me get my little cursor up here. Gotta put my pen down. Okay. Okay. So let's rock this. We're going to do the accountant method. So this is the proof. Okay. We got nitrogen plus hydrogen gives us ammonia. Yeah, grab a piece of paper out. So we know N2 is locked in at N2 and hydrogen's H2, that's built in. I can even get into why that is in a minute. Let's call it accountancy or accounting. Okay, so here's how we do this accounting method. And this is showing your work just as legit as the others. I don't like it, just my preference. I'm going to draw a line here, and I'm going to list my elements on either side. I'm going to go like this. I've got 2 nitrogens on this side, and I got 2 hydrogens on that side. And on this side, I've got 1, and on this side, I've got a 3. Okay, so the first one that jumps out at me right away is to multiply the nitrogen by 2. Okay, so I'm going to put a big 2 up in there. And if I do that, well, I got to multiply these guys by 2 as well, which turn them into 6. Which means I got to multiply that hydrogen by 3 to get 6. So that tells me the coefficient there. So that's accountancy method, okay? And what's nice about this is we can take out our green check mark, and we can give ourselves some check marks. Okay, 2 and 2, they match up. 3, 6 and 6, they match up. And that's how I was taught to balance. Cool. Let's call this a cloning method. Okay, cloning. Nitrogen, the chemistry geezer is made up, said nitrogen's blue. Okay, there's this thing called the CPK model. And those geezers are the ones that figured out or just declared that nitrogen's blue. So I'm going to draw a nitrogen molecule. There it is there. And now you know why I highlighted, because do I have to show charges for molecules? No. And so I'm going to go over here to this guy here, and I'm going to draw an ammonia molecule, like that. And so I look and I say to myself, on the left side, I've got 2 blue circles. On the right side, I've got 1 blue circle. So if I need another blue circle on the product side, well, if I do one of those, I get to have to carry 3 hydrogens with it. That's built in to the molecule. That's why knowing your chemical formula is vital, right? So I don't know, a few weeks ago, you're probably going, oh, why do I have to learn all these chemical formulas? Well, now we know, because if we mess up the chemical formula, we're not gonna be able to balance properly. So how many white circles do I have there? I mean, they're outlined in gray, but yeah, there's 6. And now hydrogen's H2, that's built in. So that means I need 3 of these. And now I do a quick check. And I go, okay, look at that. 1 molecule of nitrogen reacts with 3 molecules of hydrogen to form 2 molecules of ammonia. My buddy called this the ghosting method, but that was a long time before that term had any relevance to dating world. He would literally draw ghosts of what was there, which you can do, or you can do scratch out method. Okay, so I'm going to do the ghosting method. I'll just call it the ghosting method because it's Halloween time. You ghosted me, man. Okay, so what we do is we start off with a whole pile of reactant. Okay, I'm just going to draw, usually 6 is good. 6 of each. And the rule is you can't, once you start using it up, you got to go all the way. And then you got to keep using until you've built. And the first time you get a full build and a full use up, that's when you're done. And then you know your ratio. So we already know the answer to this question, don't we? So I'm going to draw 6 hydrogens here. And what I like about this method is that it's useful. This is the applied part. Because if I was ordering this stuff for my company, I would know how much to get. Watch this. So if we start off with 6 of each, I gave you a test tube, or, a container of 6 of nitrogens and 6 hydrogen molecules, away we go. Now I want to build an ammonia. Okay, so here's the ghosting part. There's the ghost of that. And I realized, I can't just partially use. I got to finish that off. So if I start one, I got to finish it off. So that means I'm required to, by this method, have that ghost. Now, you've drawn them, and I have this handy dandy eraser. So what you can do is the other way you can do it is a scratch out method. Okay, so I'll do the ghosting with the 1, and I'll show what you guys, if you want to use this method, which I think is better. It's a little bit more time consuming, but it's more accurate. Okay, so how many hydrogen molecules do I got to use up to satisfy these dudes? Well, there's 2 there. Okay. Or there's 1 molecule made of 2 atoms. The 1 molecule will supply me 2 atoms. But is that ammonia fully built yet? No, I need a 3rd one, don't I? Okay. So if I want a 3rd one, then I got to steal from that guy. We'll use that one up. But the problem is that I can't then partially use up that hydrogen, which means that one that I've just disappeared is now over here. So we can kind of draw the ghost of where it was. That's now, hopefully you see why the ghosting. Okay, but now the ammonia is not fully built. is it? Which means I need to use up another molecule, 2 atoms. And so again, we see 1 molecule of nitrogen reacts with 3 molecules of hydrogen to make 2 molecules of ammonia. Now this method takes a longer time. I think it's cooler because we can clearly see, do we have enough hydrogen present to do another full round? Yeah. Okay, so I'm going to do a scratch out method for you. Okay, round 2. Okay, so I'm gonna start building another ammonia, and I can't just start. I got to scratch that out, which means I got another one here. Okay, so that nitrogen molecule is gone, and now obviously I need to pull those other hydrogen atoms. Okay, so here's why I like this method. Don't be packing up yet. No way. Here's why I like this method. I just put that right there. How many more? So we used 2 molecules of nitrogen and we're done. Like we don't, careful. Okay, so this is the ghosting method or scratch out method as we might call it. Oh, sorry, I was going to demonstrate that, wasn't I? Hold up, let me fix it. So if you want to use ghosting, you can just call it scratch out, but I'll call it ghosting because that's the effect here. 1, 2, 3, 4, 5, 6. So now my question is this. We got 4 molecules of nitrogen left. If I said, hey, we got to order more hydrogen, how much would we need? For every N2, how many hydrogens does it cost? 3. 1, 2, 3, 4. We would need 12. Okay, so every method works properly. Lewis structures, don't pack up. Give me 2 minutes. If we wanted to go from the atoms to the molecules, why is pure nitrogen N2 and not just N? Well, how many electrons are in the outside shell of nitrogen? And you're writing this down so that you can do this part on the test next week so you can get a better grade next week because you understand why this is happening. How many electrons does nitrogen have on the outside of it? 5. It needs 8. So if we had just pure nitrogen in a tank and these 2 atoms got together, yeah. wouldn't they be like, hey, hold on a sec. You need 3 and I need 3. So here's how Lewis would show you what nitrogen gas molecule looks like. And here's what a ball and stick model would look like for this. Triple bond, I heard it. Love it. What do you say? I love that for you. Triple covalent bond. Okay, now let's look at hydrogen. Hydrogen only has 1 electron. And if you only had hydrogen atoms, wouldn't they say to each other, hold up, I need 1, you need 1, let's just share until we can find a better combo. Don't go. Wait for the bell. There's your N2 molecule. That's why nitrogen is N2. It's a better deal. And it's quite stable. It's 80% of the air that we're breathing. So hydrogen is going to covalently bond like that. And if we're going to do a ball and stick model, do not pack up. I'm not done. Single bond. And we call those covalent bonds. Okay, now let's do ammonia. Guys, excuse me. Third time, please don't pack up. Thank you. Okay, this nitrogen has 5 valence electrons. It needs 3. So if hydrogen's in the neighborhood, that's right, it's going to do 3 single bonds. I'm in love and hearing, I understand. That's the greatest, that's music to my ears, man. So now we just draw single bonds as dashes. And you don't have to color code them, but it helps. All right.